From St. Louis Public Radio. This is St. Louis on the Air.
Welcome to St. Louis on the Air. I'm Danny Wysentowski. Before we get to today's topics, we have two pieces of exciting news. The first is that we resume a 5-day-a-week broadcast schedule starting Monday. The second is that we've selected a new host for this show. Her name is Elaine Shaw. Elaine brings more than a decade of experience in journalism and community engagement. She's been a producer for Southern California Public Radio and 9PBS here in St. Louis. She created critical content for the Ferguson Commission's report, Forward Through Ferguson, A Path Toward Racial Equity, and she later worked on that organization's education initiatives. More recently, she served as senior manager for external communications at Big Brothers Big Sisters of Eastern Missouri, and she is the co-editor of the forthcoming Humans of St. Louis book. We're tremendously excited about Elaine becoming host of this show. She starts on November 7th and will begin hosting the show later this fall. To read more about this announcement, visit stlpr.org/host. And now to today's show. 100 years ago, scientists were confounded by light. What is light made of, they wondered, and how does it actually work? One idea came from some guy named Albert Einstein, but few took him seriously at the time because the idea was wild. He had theorized that light, somehow, was both a wave and a particle. He couldn't prove it, but the math worked out. Enter physicist Arthur Holly Compton. In 1922, in the basement of Eads Hall in St. Louis's Washington University, Compton was experimenting with X-rays, and something just didn't add up until he realized that Einstein was right. It behaved like a wave and like a particle. The discovery won Compton a Nobel Prize and changed how science understands the very building blocks of our universe, matter itself. To talk about Compton's legacy and how his discovery forever changed our view of physics, we have in the studio Erik Henriksen, Associate Professor of Physics at Washington University. Erik, welcome to the show.
Thanks. It's great to be here.
Erik, when we think about physics, we often think about Isaac Newton, forces acting on each other, a body being at rest, etc. Newton thought light behaved like a particle. Scientists later said, no, it behaved like a wave. And that brings us to this moment in 1922 where this is still a bit unsettled. Tell us about this moment in 1922 and what Compton was doing in that basement that really impacted this question.
That's right. So Arthur Holly Compton came to St. Louis in 1920 to pursue experiments on X-rays scattering off of materials, which might seem a little mundane now, but it was forefront science at the time. X-rays at the time were largely understood to be like light, a wave-like phenomenon. The experiments that Compton went in the basement and undertook showed that this was not entirely right. He discovered the phenomenon of what we now call wave-particle duality, that this phenomenon we really thought was like a wave, in fact, can behave like a particle as well. So when I talk about wave-like phenomenon, imagine you're standing at a pond, put both your hands in, start beating them back and forth on the water. You're going to see circular waves spread out from both your hands. And where those circles overlap, you'll see alternately the crests and troughs of the waves will reinforce or cancel each other out. That's a classic interference phenomenon. Light shows this. X-rays were understood to show this by the early 20s. Particle-like behavior is more like, think about playing billiards. You hit a cue ball goes and hits the 8 ball, and then they both carom off in different directions, and the cue ball has now lost some energy. So the experiments that Compton was doing clearly showed that the X-rays he was scattering off of materials like graphite were coming out having lost some energy. And there was no way to understand this classically. In the classical understanding of light, light waves don't lose energy when they bounce off of objects. Yet clearly these X-rays were.
And I think that it's so startling thinking about, having our scientists, lacking this certainty about how fundamental properties of the universe work. And the development of quantum mechanics, which were so key to this, something that is, just in my own reading of this, is the sense that quantum mechanics are not intuitive. They are not the same way as Newton, seeing an apple dropping or however that goes, seeing a force and then seeing the impact. Quantum mechanics really is, we had to look at the universe. We had to measure it and see what it did. We couldn't really figure it out just, from looking maybe at larger objects around us. how big a leap was this, and how difficult was it for scientists at the time to look at something and say, this doesn't make sense, but it's real?
It was really huge. This was an unexpected discovery. To say that something could behave both like a wave and a particle in somehow the same object was confounding then, and honestly, it's quite confounding now, but it underlies our entire understanding of the universe through quantum mechanics. So when Compton discovered this, X-rays had been thought they were wave-like. Now they have this particle-like behavior almost at the same time. This directly inspired a French physicist by the name of Louis de Broglie, who said, well, okay, if something we thought was waves is a particle-like, maybe something that we know to be a particle could have wave-like phenomenon. And so he said, what if electrons behave like waves as well? This was soon shown to be the case. And these kind of twin discoveries demonstrating that wave-particle duality was clearly a phenomenon we had to deal with everywhere directly drove the theoretical developments of quantum mechanics through the rest of the 20s, giving us the theory that we now have and we've had for a century since.
Very, very briefly, what are some of the bigger impacts that this discovery allowed us to discover? I know this is basic physics now. This is in everybody's physics textbook, but what windows did this open for us?
Yeah, that's right. This is in all of the intro texts, and you have to grapple with it one way or another. Probably one of the most important applications of this knowledge, this Compton effect by which X-rays lose energy, is in the domains of astrophysics and cosmology. When you look out at the universe with telescopes and you see the light streaming to us from distant places, for instance, in the center of galaxies, there are black holes that kind of hold the galaxies all together, and there's a lot of X-ray radiation being emitted from those places. And because of all the matter that is surrounding the center of galaxies, those X-rays are undergoing this Compton scattering effect all the time. It is impossible to understand how galaxies behave without understanding the Compton effect to begin with.
And really just it broadens our horizons by actually allowing us to get some information from these particles that are bouncing back at us. We can tell sometimes, what object it hit, how far away that went. Applications in astrophysics are, pointing these things at a planet. But, Compton the man, though, we don't know perhaps as much as we'd like to know about him, but his discoveries, he worked on the Manhattan Project. He also played banjo in some photos that I just saw this morning that are just remarkable of just him sitting in a circle of students. He also designed a speed bump that also bore his name. What did you find out that inspired you about this person and the many areas that he impacted?
Really, the thing I found in researching him in the past couple of months that impressed me the most as a practicing physicist was to be able to watch his discovery progress. It's not like he went in the lab, did one set of experiments, said, aha, wave-particle duality is a thing from now on. Instead, he had these results from scattering X-ray off of graphite. He had some data, and he had to think about it. And his first idea was just wrong. It took him about 5 or 6 months to figure that out. He got some better data. He stared at it for a while, came up with another explanation. It was also wrong. It took him another month or two to come up with the final understanding of a quantum theory of scattering, which incidentally he first presented to his physics class in November 1922, so just a century ago. So his students were the first ones to hear about this discovery. So I really got the sense that, day by day he's down there struggling with the data, trying to understand what is this telling me about the universe. But it wasn't, just a single aha moment.
No. And there is so much to this story, the man, the science, the discoveries. And for more, there are several events being hosted this month at WashU for the Compton Centennial Celebration. More information, you can find that on our website at stlpr.org/show or at physics.wustl.edu/events. Erik Henriksen is an associate professor of physics at Washington University. Erik, thank you so much for being here.
Thank you. This is great.
This episode was produced by Danny Wysentowski.
Audio engineering and podcast design by Aaron Dorr. Our production intern is Avery Rogers. Our executive producer is Alex Hoyer.
St. Louis on the Air is a production of St. Louis Public Radio. Understanding starts here.
Our podcast proudly supports St. Louis artists by using music from Life Creative Group.
Do you find yourself regularly listening to episodes of St. Louis on the Air? Suggest us to a friend you think might enjoy our conversations, and leave us a review and rating on Apple Podcasts on the App Store. It's the simplest way to help people discover our show. Thank you.
St. Louis Public Radio is a member-supported service of the University of Missouri St. Louis.
Support comes from the Missouri Forest Products Association. Missouri produces wood pallets, railroad ties, white oak barrels, hardwood floors, and more. Details on the variety of products made in the state are at choosewood.com.